So we've covered calculating roots of complex numbers. What I'm going to do here, I've just got a couple of questions for you. I'm going to go to the next slide, show you the questions. I want you to pause the video, have a crack at them, and then come back and check you're working with the answers I'm going to present. So here you go. All I want you to do is quite simply solve the following pair of equations. So the first one, z cubed equals 1 plus I. Second one, z to the power of 4 equals 81i. So pause the video and have a crack. Just remember though, if you're working with a decimal number, go to 3 significant figures. So the first one, z cubed equals 1 plus I. So first thing we have to do is write it in polar form. So we need the r and we need the theta. So r for this one is equal to the square root of 1 squared plus 1 squared. So the coefficients of a real and their imaginary section. So that quite simply gives me root 2. Theta for this one is equal to tan minus 1 of the y over x. So in this case, y over x are both 1. So it's just tan minus 1 of 1, which is pi over 4. So there you go, I've got the two parts. I can now write it in polar form. So I know that z cubed is equal to the square root of 2 bracket cos of pi by 4 plus I sine of pi by 4. Now we want to solve it, so we're going to take the cube root, but remember, we're going to get multiple solutions to this. We know how many based on the power. We know we're going to get 3 solutions overall. We just have to make sure we write it in the format such that we can calculate it. So I know I'm going to have z equals the square root of 2 bracket cos. Now remember, we have to write this as pi over 4 plus 2k pi. Takes into account all the solutions by extending it to the negative n pi to n pi, which then gets brought down when we use De Moivre's theorem to bring the power in. Then plus I times sine of the same thing. So sine bracket pi over 4 plus 2k pi. All of that to the power of a third. So now we bring the power of a third in. Again, use De Moivre's theorem for this. So the root 2 is going to go to a third. So root 2 to a third, that's the equivalent of 2 to the half to the third. So that's going to be 2 to the power of a sixth. Now this sort of one here, 2 to the sixth, just keep it as that. We then have to take this bracket here and sort it. Well, if I'm going to sort the bracket, that's going to be the equivalent of 1/3 times pi over 4 plus 2k pi, which is then going to simplify and give me pi over 12 plus 2k pi over 3. So my brackets here for the two parts I can write as cos of pi by 12 plus 2k pi over 3. I've then got plus I sine of the same thing. Pi by 12 plus 2k pi over 3. So there we go. I've got the generalized form. I now know how I'm going to calculate the solutions. I want 3. Remember, k goes from 0 all the way up to n minus 1. Now for this one we know n is 3, so my 3 solutions for this one are going to come when I do k equals 0, k equals 1, and k equals 2. So if k is equal to 0, my first solution, z1, that's going to equal 2 to the power of a 6 outside. That's not going to change in any of them. We then put k is equal to 0 in here. That disappears, and I get cos of pi by 12 plus I sine of pi by 12. Second solution, when k is equal to 1, this time is going to be z2. Again, 2 to the power of a 6th outside. And then inside the bracket, it's going to be cos, I've got pi over 12 plus 2k pi over 3, k is 1, so it's pi by 12 plus 2 pi over 3, so plus 2/3 pi. What that's going to give me is 9 pi by 12. So it's cos of 9 pi by 12 plus I sine of 9 pi by 12. Third solution is going to be given by k is equal to 2. So z3 is going to equal 2 to the power of a sixth times cos, and again, sort what's in the bracket using this format here. So it's going to be pi over 12 plus 4 pi by 3. That's then going to simplify and give me 17 pi over 12 plus I times sine of 17 pi by 12. Now remember, at this stage we need to bring this back into our negative pi to pi range, so I'm going to take 2 pi off of each of those. So that's going to give me 2 to the power of a sixth bracket cos, and when I take 2 pi off of it, what I end up getting is negative 7 pi over 12 plus I times sine of negative 7 pi over 12. Now again, remember, we don't like the negatives in the bracket. They are associated with the angle. So it's going to be 2 to the power of a sixth bracket cos 7 pi by 12 take away I times sine of 7 pi by 12. Job done. So there you go, I've solved it there. I've got my 3 solutions for z equals 1, for z2, and for z3. So there you go. That's my 3 solutions for this one. Next question was z to the power of 4 equals 81i. Again, I've got to start by writing it in polar form. Same idea as before, and then we work it through from there. So for polar form, first thing I need is my r, my modulus. Going to equal the square root, well, of 0 squared plus 81 squared. So it's square root of 81 squared, quite simply 81. And then my theta is going to be tan minus 1 of y over x, which in this case is going to be tan minus 1 of 81. Now tan minus 1 of 81 ends up giving me 1.557 and then a whole spiel of stuff after that. So I'm going to round it, and I'm going to stick with 1.56 for my calculation. I'm going to stick with 3 significant figures throughout. Sometimes it may give you different rounding depending on how many decimal places it's got. Stick with whatever they give you or ask you for in the textbook. So there you go, I've got my angle there. So from that, I can write that z to the power of 4 is equal to 81 bracket cos of 1.56 plus I times sine of 1.56. What I can then do is take the 4th root of both sides. So I know then that z is equal to 81 to the power of a quarter bracket cos of 1.56. But again, remember, we want to take into account every single solution available. Z to the power of 4 is going to have 4 solutions. So this is where we need to make sure we include the plus 2k pi. We've then got plus I sine of 1.56 plus 2k pi there as well. And that, again, is to the power of a quarter. So 81 to the power of a quarter, well, that quite simply gives me 3. So it's going to be z equals 3. I've then got cos of a 1.56 plus 2k pi, all to the power of 4. So that's the equivalent of doing a quarter times 1.56 plus 2k pi. Now the 2k pi part I'm going to just keep written as a fraction. The 1.56 I'm actually going to do the calculation. What that then gives me is 0.39 plus pi over 2 times k. So in here, what I'm then going to write is I've got cos of 0.39 plus k pi over 2. That's then plus I sine of 0.39 plus k pi over 2. So I've got my general form for z. I can now get all of my solutions to it. I've got 4 solutions, and again my 4 solutions are going to come dependent on the value of k. Because it's 4, I know that I'm going to have a solution for k equals 0, k equals 1, k equals 2, and k is equal to 3. I just have to get all 4 of them now. So k equals 0, I'm going to substitute that in. Let's get z1. My first solution is going to be 3 bracket cos of 0.39 plus I sine of the 0.39. Second solution, z2, what I have to do in order to get that is substitute in k equal to 1. So in this case, I know z2 is going to equal 3 bracket cos. This time though, it's going to be cos of 1.96 plus I times sine of 1.96. Third solution, given by k equal to 2 being substituted in, z3, that's going to equal 3 bracket cos of 3.50 plus I sine of 3.50. Now, you'll notice that these two are out with the range for what we want. So what we have to do is bring them back into that range. So I'm going to take each of these numbers, the 3.50, and what I'm going to do is I'm going to subtract 2 pi from it. And if I subtract 2 pi from it, what I end up getting is negative 2.78. If I then substitute that back into here and use the rules for getting rid of the negatives, so just make this cos of 2.78 and make this a take away, what I end up getting is that then gives me 3 bracket cos of 2.78 take away I sine of 2.78. So that's solution 3. Solution 4, given by when k equals 3 is substituted in, z4, that's going to give me 3 bracket cos of 5.10 plus I sine of 5.10. Now again, this is out with the negative pi to pi range. So again, what I'm going to do is I'm going to take away 2 pi from this to bring it back into the range. If I take away 2 pi from this, that ends up giving me negative 1.18 after I've rounded it. If I then substitute it back into here, and again do the same as I've done here with the negatives to get rid of them, what I'll end up getting is 3 bracket cos of 1.18 take away I times sine of 1.18. So there you go, that's me got 4 solutions for that one, which I was expecting to get from the question. So when we're solving these sorts of equations, what we have to do is we have to remember all of these steps. Get it in polar form first, then take the root of it. So in this case it was to the power of 4, so I took the 4th root of it. That tells you how many solutions you're going to get, and you get the solutions by getting it in the generalized format. So your theta plus 2k pi, dividing it by the n, so the power that we're going to be taking, and then substituting in for k from 0 all the way up to 1 less than what you've got as your root. Once you've done all of that, you'll then get your final set of solutions, which are given by that. And make sure with the final set of solutions, you take away your 2 pi in order to get it back into the range that we want. So you have to make sure your final solution is in the range negative pi to pi inclusive. So make sure you take that all into account.